Okay, so those two examples that I was just talking about, beryllium chloride and carbon dioxide, not their angles not being explained by valence bond theory, there's got to be something else going on. And so what they've kind of come to the conclusion is that we're still getting orbital overlap. So this is kind of under the umbrella of valence bond theory. But what's happening to those orbitals is they are becoming hybridized. So I'm going to talk about what hybridization is. Hybridization is the mixing of atomic orbitals and molecules that can't be described by overlap. So if the overlap doesn't explain this, then they must have hybridized orbitals. So what is a hybrid orbital? That's what I'm going to get into. Okay, like I said, this should be 180 degrees according to Vesper theory, right? So what's going on with the overlaps there? Okay, so beryllium looks like this. We got 2s2. Now 2p is there, there's nothing in it, but we could excite an electron. We did excited electrons in lab, right? One of the electrons could get excited. We're going to call this promotion. So now we have a 1s1 and a 2p1. Okay, that's definitely possible. So that's what the beryllium did. Now over here, I've got chlorine's orbital diagram, right? Chlorine's valence electron, this is the one that's missing one. This one needs an overlap in order to be full and happy. So what we do is we take the 2s and the 3p, and it doesn't work to make a bond similar to the 2p and the 3p. And I know that's kind of confusing, but the 2s, we're saying that this 2s2 would need to bond with the 3p, and that this 2p would need to bond with the other 3p of the chlorine to get this to work out. The problem with this is that these aren't the same. Notice they're not equal, but these bonds should be exactly the same. So like, how is this going to happen? So what happens, like I said, is one of these electrons gets promoted into here. And now these two orbitals are going to be hybridized. They're going to kind of come together and become new orbitals. So instead of being a 2s and a 2p, so an s and a p, they are now called sp orbitals because it's made of an s and a p, and they are the same. They are similar in energy, and now we have 1 and 1. So these two have become, instead of this one being an s and this one being a p, they have now been hybridized, and we get two sp orbitals, and those are the ones that can do the bonding. Okay, so then these two are going to be able to overlap. So they're now called sp. Use these to bond with chlorine. This one can bond with one chlorine. This one can bond with another chlorine, and they will be exactly the same now. So we can get this nice even distribution of electrons. And those two bonds on beryllium will be the same. Okay, so the hybridization part is really what's going on here. These are becoming these. Okay, now three-dimensional wise, what I kind of want you to look at is these are the orbitals we're talking about. So for beryllium, right? Beryllium is the one having the hybridized orbitals. We have a 2s and a 2p, right? This is the 2s and the 2p. The 2p didn't have anything in it. We promoted one, so now you have these two. When we put them together, we kind of mush them together, we make hybridized orbitals that look like this. Now they look like this. So instead of being a circle and a dumbbell, they look like this, which are exactly the same. So now one can go on one side, and one can go on the other. So that was the 2s, this was the 2p. When they hybridize, we now get these that are 180 degrees from each other, and those can bond with the chlorine p orbitals that need to be bonded. You get 180 degrees. Now you do not have to be able to explain all of this. You just have to be able to tell me that it is sp hybridized. So I'm going to go into a couple more examples, then I'm going to kind of tell you an easy way to figure it out. Okay, so for example, I could say, determine the number and type of hybrid orbitals necessary to rationalize the bonding in BF3. Okay, so in order to do this, the first thing we need to do is draw the Lewis structure. Just always draw the Lewis structure. BF3 looks like this. We would expect it to have 120 degree angles, and it has 3 bonds, and all of those 3 bonds need to be the same. Okay, so to prove or show the hybrid orbitals necessary, you're going to count the number of electron domains. Okay, boron has 3 on the central atom. This is the number of hybrid orbitals or things that need to overlap. If you got 3 bonds, I need 3 overlaps. Okay, it's necessary to account for the molecule's geometry. So if I need 3 domains, I need 3 bonds or domains. An electron pair can count as well. We need that many to overlap. So if you look at boron's electron configuration, we need an s and 2 p's to make instead of an sp like we were talking about before, if you hybridize one s and two p's, you get sp2 because it's made of an s and two p's. So what you're looking at here, this is the ground state orbital diagram for boron, okay? So what we did is if I need to make 3 bonds, right? Currently, in its regular ground state electron configuration, this one here is the only one that would want to bond, to have 2 in there. So if I promote one, right, that's called promotion, now I would have 1, 2, 3 orbitals that need 2 electrons and can share and overlap and bond. So I would have this S and 2 of these P's. You hybridize an S and 2 P's, you get sp2 orbitals. Okay, so we maximize the number of unpaired valence electrons by promotion, which is what I was showing you here. This turns into now this. These are the 3 that get hybridized, and you have sp2. So you combine the necessary number of atomic orbitals to generate the required number of hybrid orbitals. That just means if I need 3 bonds, I need an S and 2 P's, so sp2. If I needed 2 bonds, like our example before, I need an S and a P, so it's called sp. That's it. Place the electrons in the hybrid orbitals, putting 1 electron in each orbital before pairing any electrons. So now that these hybridized, I have 3 sp2 orbitals. This guy's still empty over here. And I have 1 in each, so each of these can overlap. And then this is what they look like. This is what they look like. And then they can do all their bonding with that 1 electron from fluorine. Okay, so it works kind of the same way. So maybe try the next one on the next page kind of by yourself, and I'll walk you through it. Okay, so for these 2 examples, it says determine the number and type of hybrids necessary to rationalize the bonding in CH4. Well, CH4 has 4 domains. I drew its little dot structure, so it needs 4 orbitals. You always start with S, so I need an S and 1, 2, 3 P's. This is sp3 hybridized. That's it. Now, if I wanted to show it with the electrons, this is carbon's electron configuration. Notice there's only 2 here that would be able to bond, but it's making 4 bonds. So I promote 1 over here. Now I have an S and 1, 2, 3 P orbitals that are going to hybridize. These are the ones that are going to do the bond. So if I have an S and 3 P's, I have sp3 hybrids, 4 total orbitals, ready to go. That is literally it. Okay, PCl5. So you add 1 more. I need, looking at this electron configuration, I have 5 domains, so I need 5 orbitals. This is the electron configuration, the valence electrons in phosphorus. Notice I only have 3 that would be able to overlap and bond. So I promote 1. So now I have an S, 1, 2, 3 P's, and a D. So an S, 3 P's, and a D is called sp3D hybridized. That's it. Now I have 5 that can actually bond. So the summary of hybridization is really just that it explains why they bond, because you want 2 electrons in each orbital, right? So in order to do that, sometimes the electrons have to move, and then they can create these hybridized orbitals, and they will bond, okay? What you need to know is that if I have 2 domains, I'm going to be sp hybridized. If I have 3 domains, I'm going to be sp2 hybridized. Every time you add a domain, you add an orbital that needs to be hybridized. So if it's 2, it's an S and a P. If it's 3, it's an S and 2 P's, so on and so forth. And you only have an S and 3 P's because there's 3 orbitals and a P, and then D can go up to 5, but this is all we're going to see because we're only going to do 6. So if you take away anything from this lecture, it should be this little chart right here. 2 is sp, 3 is sp2, 4 is sp3, 5 is sp3d, and 6 is sp3d2. And that is it. So in example number 7, again, explaining the angles. I drew ammonia here, has 4 domains. So I know if it has 4 domains, it has to be an S and 1, 2, 3 P's. So it's called sp3 hybrid orbitals. Now I drew it out. This was nitrogens, but I only have, I drew nitrogen so that it could bond here. Notice I didn't have to do any promoting because it already had 3 places to overlap and bond. And then its other 2 electrons are just chilling here on nitrogen. They didn't go anywhere. So these 3 are overlapping with the hydrogen ones. Now, why does that make it a 107-degree angle? And that's because of my 4 domains, essentially. But if I have these 5 trying to get as far away from each other as possible, or really these 4, I'm going to be close to 109.5, which is 107, because 109.5 is the angles for something tetrahedral where you have 4 things trying to get as far away from each other as possible.